Okay, thank you, Diane. So as Diane mentioned, we will be talking about PCC, Policy and Charging Control Architecture. So basically this is a separate network that connects to the LTE EPS, Evolved Packet System, so that we can provide end-to-end quality of service and charging for the user. Briefly, my background. I have graduated from Virginia Tech with a PhD in electrical engineering, where I did research on handoff algorithms using neural networks and fuzzy logic. I have worked for Nortel and Huawei in the past, where I worked on ICE95, 1X, UMTS, and 1X EVDO products. For almost 7 years, I have been teaching for Award Solutions, and I teach various technologies, LTE, WiMAX, UMTS, HSPA, etc. Again, welcome to the session. Your questions are most welcome. No limit on the number of questions that you can ask. So please maximize the use of Q&A box in live meeting. Your question will be answered in the order it was received. Okay, so just start typing your questions. We will also give you some opportunities to ask questions using the audio bridge. We will have 2 short 10-minute breaks also. Okay, so before we begin, if you spend few seconds on telling me a little bit about yourself, your current type of work. Ten seconds to go. And we appreciate your feedback in all the polls. Okay, so let's say about 30% system test integration, 25 each customer support, systems engineering. Okay, very good. One more question. 30 seconds for this one. What kind of details you are looking for today? Okay, so about 60% medium degree of details, and about 40% lots of details. The material that we have put together is aiming for medium degree of details, not too light, not too heavy, okay, in terms of technical details. So anytime you want something more than what is available in the presentation, please ask questions. Asking questions is the best way to customize this session for you. Okay, so please ask questions. Okay, thank you for your feedback. So this is what we have planned for today. So we will talk about the overall architecture of PCC, Policy and Charging Control. And by the way, you should have the PDF file that has the copy of the presentation. Now, toward the end, we have an appendix that has acronyms. So either you can look up there or you can always ask me a question. Okay? So acronyms are all defined toward the end of the PDF file. So main network elements within the Policy and Charging Control architecture. And as I said, that is for end-to-end quality of service. Now, what are some of the characteristics of QoS as far as LTE is concerned? There is something called QCI, Quality of Service, Class Indicator. Now, we will see that in LTE, we have 9 different levels of QoS. In basic UMTS, we have 4 levels, but now that goes up to 9 levels. Okay. So we will see the main characteristics of QCI. There is something called TFT, Traffic Flow Template. So when a packet arrives from the outside world to the PGW, then the PGW, the Packet Data Network Gateway, has to figure out where to place that incoming IP packet. Should it be placed on a GTP tunnel 1 or 2 or 3 or what? So that kind of decision we have to make at the PGW, and the concept of TFT helps the PGW figure out where that packet should be placed. So we will see what is inside a TFT. Within the PCC, we have 2 major network elements, PCRF and PCEF, policy and charging rules function, policy and charging enforcement function. So basically, for a given session could be a voice or IP session. For such session, the PCRF will create rules on QoS. For example, what kind of data rate we should provide, what kind of delay is acceptable for that kind of session. And once the PCRF has made those decisions, it will provide those decisions as part of a rule, quality of service rule, to the PCEF. And the policy and charging enforcement function will make sure that those rules are followed. So we will talk about those 2. And we would see how a dedicated bearer is set up so that we can meet the QoS that we have promised to the user for a given service. And finally, toward the end of the session, we will spend a few minutes on charging. So let's say user talked for 10 minutes, then we have to figure out, okay, how many cents per minute, and accordingly we would create a bill for the user. So how do we charge the user for the service? So there are 2 main mechanisms, online and offline charging, and we will talk about those. So that's what we have as our agenda today. So let's start going into the specific details. First, we will talk about the architecture. Okay. So in terms of the architecture, we have so-called application function. We have PCRF and we have PCEF. We have some kind of database, SPR, subscription profile repository. So those are the main network elements: application function, PCRF, PCEF, and SPR. Now, the application function is basically in LTE is implemented by so-called proxy, call session control function, proxy. Now this is one of the nodes in the IMS network, IP Multimedia Subsystem. In one of the sessions, we will talk about IMS in more detail. But for now, it is good enough to know that this proxy, call session control function, is part of an IMS network. So for example, the operator would have a separate network, IMS network, Verizon, its own IMS network, AT&T, its own IMS network. So an operator basically has its own IMS network. And that IMS network connects to the LTE EPS, Evolved Packet System. So application function is implemented by the proxy CSCF, which is part of the IMS network. And IMS element proxy CSCF connects to the PCRF through the RX interface, and the PCRF talks to the enforcement function via GX. Now, in LTE, Who implements enforcement function? The PGW, Packet Data Networks Gateway. PGW acts as PCEF in the LT system. A subscription profile repository, even though it's mentioned as some kind of separate box, some database, in practice, normally it would be part of HSS, Home Subscriber Server, HSS. Okay. Now, I may ask you some questions periodically. Okay. So, feel free to type your question through the audio, Q&A box. Using audio grid would be too much. So, to give me your answer and question through Q&A box. So, HSS, Home Subscriber Server. So, please let me know how HSS is used. What is the use of HSS? Just give me your answer through Q&A box. What is the use of HSS? Do you remember that? Okay. Let me see if I have anyone trying to give me the answer. Use of HSS. We have 45 students. Okay, authentication, very good, very good. I got a lot of answers. Okay, thank you. Yeah, so it's a subscriber database, very good. Subscriber database, and it will help us authenticate the user because information about the secret code, secret key for the user is stored in the HSS. HSS knows, is it a platinum user, gold user, what kind of services the user has subscribed to, things like that. Okay. So those are some of the things we can do with HSS. Okay, so thanks for your answers, and looks like we got one more question. Okay, is there any communication between the charging system and PCRF? Actually, let's wait toward the end of the session. Okay, we will answer that question. But basically, yes, the charging system and the PCC, they sort of communicate. And the interfaces that we have are those GY and GZ. Okay. So basically, from the HSS, okay, we get some information about the subscriber because HSS has subscriber database, and the operator AT&T Verizon, they would come up with some kind of rules on charging, and they will put all those rules in the PCRF. Charging rules. Okay. So for example, if it's a voice over IP type session, then let's say 10 cents per minute, something like that. We can have that kind of rule for charging installed in the PCRF. So an operator would do that. Okay, charging system just processes some kind of charging data records. So we will talk more about that later. Okay, let me see. Okay, very good. Now, anytime my answer is not satisfactory, maybe you want more details, you want better explanation, please follow up your question with additional questions, okay? Okay, now, let's see at a high level, what are the main functions of these various elements? And as we go through the slides, we will learn more and more about how QoS is implemented. Now, let's say we have a user that starts some kind of application that is related to IMS network, operator control services, when I say operator controlled, what I mean by that is AT&T, Verizon, they know what kind of service you are using, okay? Because they have their own IMS network. An example of such service is voice over IP. So let's say we have subscribed to, we are AT&T subscriber, and we have subscribed to AT&T voice over IP. Or we are a Verizon subscriber, and we have subscribed to Verizon voice over IP. So when we dial some kind of number on our device, then our device would send SIP signaling messages, session initiation protocol, SIP signaling message. For example, invite, that is one of the messages. So SIP signaling messages are sent by the device all the way to the IMS network. And here in this picture, let's see how our SIP signaling messages would be reaching the IMS network. It would go from UE to the E node B, Evol node B, then to the serving gateway, SDW, serving gateway to the PGW, and then we have this private IP network that is owned by the operator, AT&T, Verizon, like that, and it will reach this proxy, all session control function. Remember, that is part of the IMS network. So basically, when we use some kind of application, SIP signaling messages would be reaching the IMS network. So this is an example of an operator control service, such as voice over IP. So then this application function would extract so-called STP from SIP signaling. STP is session description protocol. Session description protocol. So that will basically indicate requested quality of service. For example, it would say that we are using speech codec AMR, adaptive multi-rate speech codec, and it would say the data rate that we request is perhaps full rate 12.2 kilobits per second. So when we have some SIP signaling message, such as invite, inside that SIP signaling message we have information about the QoS in the form of STP, session description protocol. And that information is extracted from SIP signaling messages by the application function, which is basically implemented by the proxy. Now, the proxy would forward that STP to the PCRF, policy and charging rules function. So inside the STP, we know that, okay, we need to use AMR speech codec, and we have requirement for 12.2 kilobits per second. Now, the question is that application allowed or not? Has the user subscribed to that kind of QoS, that kind of application? So we have to ask this HSS SPR that is this QoS allowed, this kind of application allowed or not? And in the HSS SPR, we know that we have the subscriber information that, okay, we will say this is okay. We allow that kind of application. Voice over IP is allowed, and user is allowed to use a 12.2 kbps data rate, no problem. So now the PCRF will create a rule specifying the quality of service for that specific session. Since this is a voice over IP session, then the data rates, etc., QoS characteristics, they are all corresponding to a voice over IP session. So we would say that, okay, we need to guarantee data rate of 12 kilobits per second, 12.2 kbps. What kind of QoS we should give? So it would decide QCI number number 1. Quality of service, class indicator 1. Remember what I said, there are 9 levels of QoS in LT, 9 levels. So out of those 9, QCI 1, 2, all the way up to 9, our PCRF has chosen number 1. And I will show you a table that summarizes all the QoS characteristics. But QCI 1 is for real-time services such as voice or IP. So now we have created a rule in the PCRF that for this session, we need to guarantee the bit rate of 12.2 kbps, the QoS class, QCI is number 1, and that information goes to the PCEF, enforcement function. Now the enforcement function is implemented by the PGW. Now the PGW checks, do I have any existing EPS bearer, evolved packet system bearer, that can meet this kind of QoS? And let's say in our example, there is no such EPS bearer in existence. So then the PCEF says, okay, let me initiate setting up of a new bearer that would give me the QoS that I need for this application. So new dedicated EPS bearer with those QoS characteristics we need to set up. So now PCF initiates setting up of a new dedicated EPS bearer. Okay. And then we will work with other EPS elements, EPC elements such as MME, serving gateway, eNode based part of EU-Trans. So we will have some cooperation among all those entities so that we have now a new EPS bearer between the UE and the PGW that includes some radio bearer, new radio bearer, new S1 user plane bearer, and new S5, S8 bearer. Okay. So those are the main functions that application function, PCRA, PCF, and SPR carry out. Okay. And once the session is done, then we have to charge the user. So depending on the type of charging, online charging, offline charging, we would be using those interfaces GYGZ with the online charging system OCS, offline charging system OFCS. We will have coordination between PCC and charging system so that we can charge the user in a proper fashion. We got one question. Does SIP signaling message go through STW? Yes. Okay, let me draw something here. Okay, so short answer is yes, but let me just explain something. A very good question. And I will use something called Windows Journal. Right on the top left corner, you will see Windows Journal. And I will send you a soft copy of these journal notes. Okay. So SIP signaling. Basically, this is treated like user traffic. User traffic, email, web page, right? Those are examples of user traffic. So when we have SIP signaling, which is for session setup, IP-based session setup such as voice or IP. Okay. The SIP signal is treated like user traffic, and user traffic, as we know, passes through the radio bearer, the S1 user plane bearer, and the S5, S8. So our SIP signaling messages, they are traveling this way. Okay, and they will be forward it to an appropriate entity, let's say some IMS network proxy, so that the IMS network can do the further processing. So yes, SIP signaling messages is just like regular traffic, email, web page, etc. And we are not using the non-access datum signaling with MME. Okay, so that's very, very important. And thank you for your question. Very good question. Okay, and when I'm writing on the journal, if you do not see the full view, function key F5, you can go into full screen mode and you can come back to the normal mode, again pressing the same button. Okay, so let's get back to our slides. Okay, so we just summarized the main functions of various network elements that are part of the PCC. Now there is one additional element that sometimes you would see, and that is so-called BBERF, bearer binding and event reporting function. Now it will normally not be present when we are using GTP tunnels. For example, what we mean by here is I have serving gateway and PGW. So when the S5 interface, or S8, if this is GTP, then there is no need for bearer binding event reporting function. Okay. However, in some cases, and that is a typical case, okay, that is the typical case. This is, so usually no BBERF, because current commercial network, we are using GTP on S5, S8. Okay, so then you do not have BBERF. However, one specific example where you will see BBERF is when we have interworking between LTE and EHRPD. Okay. So in that case, we will have this BBERF. So what does it do? Okay, first of all, we have one separate session on interworking between LTE and 1X EVDO or EHRPD. So we'll see more details at that time. But basically, in EHRPD, we have upgraded PDSN which is called HSDW. And HRPD serving gateway acts as BBRF. So when the user tries to access the LTE core network via 1X video, then this HRPD serving gateway will tell the LTE network that, oh, there is this user trying to use some services. So we are using, in that case, 1X video air interface, but we are using the LTE core network, for example, PGW. Then we are using the PCC architecture for QoS. So in that case, the PCRF will be informed by this BBRF that one kind of event. What kind of event is this? The user is accessing the LTE system. The user has just started using the network for some services, and that is the main function. We may want to charge differently for different radio access. LTE, we may want to charge one way, For 1x video radio access, we may want to charge the user another way. So there are these kind of events that change in the radio access technology. So when these kind of events occur, then we have to get that knowledge passed to the PCC so that we can do appropriate kind of charging. Okay, so that is basically one of the functions of BBERF. Okay. Now we have got a couple of questions. Again, do not worry too much about charging at this time, because toward the end of the session you will get a very clear view of how we will do the charging. Okay, but basically we have PCRF talking to the PCEF, and the PCF will work with the charging system. So we do not need to have direct communication with the OCS. Okay, so our PCC talks to the charging system. So think of PCC like an integrated architecture, and that PCC talks to the charging system. Okay. So we could have chosen PCRF talking to online charging. We could have asked PCEF to talk to the charging system. Right? It would have been a decision about what kind of architecture we want to have, what kind of interfaces we want to have. But in the architecture that we have chosen, the enforcement function talks to the charging system. Okay. And you are worried about some thresholds being exceeded. So basically, PCEF will make sure that data rates are not exceeded. And in terms of user using, let's say, more data than allowed, or talks for a longer time than what is allowed by, let's say, the amount of credit the user has. So do not worry about all those things, because periodically we will be getting authorization for the number of minutes the user can talk for, based on how much money the user has in the account in case of online charging system. Okay. But do not worry about the details. Hopefully you got short answer, but you will get more accurate answer toward the end of the session. Does MME have any role in this PCC architecture? For end-to-end QoS, the way we have described, no, MME does not have any role in QoS itself. However, we have to establish a new dedicated EPS bearer. And MME will help us in put all those pieces together, meaning radio bearer, we have to set up S1 user plane, S5 bearer. We have to set up all those bearers. So MME will help us set up all those bearers, but it does not control the QoS itself. The QoS control is essentially with the PCRF. So in terms of what is the data rate allowed, what kind of delay we want to guarantee, all those QoS parameters are controlled by the PCRF, because PCRF constructs QoS rules based on the profile of the subscriber that we get from the HSS SPR. But in terms of direct control, only PCRF is in charge. MME does not really control. MME just helps us set up the required bearers to have an end-to-end EPS bearer. So MME does not control QoS, it facilitates setting up of a new EPS bearer. Thank you for the question. Some examples of the functions the PCC architecture performs. Binding. So we have service data flow, SDF. For example, a voice or IP session, interactive gaming session. So we have some kind of application, service data flow, and we have to map that onto a specific IP CAN bearer, IP connectivity access network. IP is just Internet Protocol, IP connectivity access network. There is so-called IP CAN bearer. For LTE, this is nothing but your EPS bearer. So as an example, we will say that a voice or IP session is mapped onto bearer number, let's say 10, EPS bearer number 10. So we have done so-called binding between a voice or IP session and a specific EPS bearer number 10. So we have placed voice or IP session onto EPS bearer number 10. That is called bearer binding. Then gating control, the gate is open or closed. Open means that application is allowed. So user has, let's say, subscribed to that kind of application, then the gate is open. And if the user has not subscribed to something, the gate will be closed. So application is not allowed in that case. So if you are trying to use AT&T Verizon voice or IP, but you have not subscribed to that, then the gate will be closed for that application. Who is opening and closing the gate? Your PGW. Right? Because the IP packets are always traveling through the PGW. So if you are trying to use a service you have not subscribed to, then PGW will block that packet. It will close the gate for that specific application. So if you are subscribed to something, no problem, your gate will be open for that service. So PGW opens and closes the gate depending on the subscription. We have to set up the EPS bearer. So PCC helps us with that because whenever there is a need to set up an EPS bearer that has to meet certain QoS requirements, then a new dedicated EPS bearer would be established. So PCEF, the enforcement function, would initiate setting up of such dedicated EPS bearer. So that is initiation of such bearer. Event reporting, as I mentioned, one example is change in the technology. So LTE is one radio access technology, eVideo, UMTS, etc. So depending on that, we may want to have different kinds of charging for the user. So that is that. And QoS control. So the PCRF is giving the rules related to the QoS. So that is controlling the QoS. So PCC is in charge of controlling quality of service. Very, very important. Okay, time for me to ask you a couple of questions. So please participate in the poll. I will give you about 2 minutes, a minute or two. In the meantime, Diane, is my voice okay?
Yes, it's coming through fine.
Okay. Okay. Okay, I will wait for 30 more seconds. Please participate in the polls. In democracy, we need participation. We have democracy here. So please participate. Everyone's vote counts. 10 seconds to go. Okay, let's share the results. Okay, so almost all of you got it right. Controlling end-to-end QoS, okay, quality of service. See, the default bearer is normally not within the part of PCC responsibility. For example, when you power up, we may have already a default EPS bearer with some EPS. Okay. Central to the idea of providing quality of service is QCI, quality of service class identifier, QCI. So here we will see what that is. Okay, before we go into the QCI details, let's understand some terminology. So we have two kinds of bearers. We have default EPS bearer and we have dedicated EPS bearer. Okay. Default EPS bearer gives always on experience to the user. So the user feels connected to the network at all times. So even if you are sitting idle, no data activity, and after a while you click on Internet Explorer window or you open up your inbox, your emails application, then you can resume your data transfer very, very quickly. So default bearer is always there. Even when you are in the idle mode, we have some part of the default EPS bearer already there. So default bearer gives always on experience. However, we have this dedicated EPS bearer, and dedicated EPS bearer helps us provide stringent quality of service control. So if you want to guarantee some data rates, you want to guarantee some kind of delay, then dedicated EPS bearer is the one that you need. Because if you look at default bearer, it is a non-guaranteed bit rate. Okay. So we may say the user, I will give you up to let's say 10 megabits per second for this default bearer. But it is up to. We may give even zero, nothing for a long time. So if you are interested in guaranteeing some bit rate, guaranteeing some data rate, then the default bearer is not adequate, because default bearer does not give you any data rate guarantee. So in that case, dedicated bearer is required. As an example, if you are doing a voice or IP session, then we need to have some data rate guarantee. So as an example, whenever we are talking, the vocoder is creating the speech frames for us, then we need to guarantee 12.2 kbps. So we need to have radio resources reserved for that kind of data rate. So in guaranteed bit rate, we have guarantee of data rates, even latency. We can control more tightly in the case of GBR, in case of dedicated bearer. So we have to basically reserve resources. So that's the guaranteed bit rate. Because in wireless system, whenever you want to guarantee something, you have to reserve resources, especially on the radio interface. On the other hand, if you have a non-guaranteed bit rate type bearer, then no need to reserve any radio resources. So whenever our eNodeB scheduler has resources available, we will give those resources to the user. So if there are multiple EPS bearers, then we can say that the aggregate maximum bit rate, the total limit could be, let's say, X megabits per second. So it is possible to specify upper limit on the data rate that we can allow for multiple bearers together. So default bearer, even when we power up the UE, we will have those established. And the dedicated bearer, based on the need, we would establish. But the main idea here is the default bearer, there is no data rate guarantee. And if we have a dedicated bearer, there may or may not be data rate guarantee, but at least you can control the QoS tightly. You will have the possibility of reducing the end-to-end latency. We have got a couple of questions, so let's take care of those. So bearer binding event reporting. So as I said earlier, do not worry about that. Typically it is not there. So BBERF you will not see in an LTE network if it is just talking to UMTS or a standalone LTE network. There is no need, because in current commercial deployments, and we expect that to be the case for a very, very long time, is that between SGW, PGW, we have S5S8. And on that S5S8, we normally use GTP. So whenever you use GTP on S5S8 for an LTE network, you do not have BBERF. However, if you use PMIP proxy mobile IP on S5S8, yeah, then you will have BBERF. But I have not seen any operator doing PMIP on S5S8. So that's why you will normally not see BBERF in an LTE network. However, an exception is interworking between LTE and 1X eVideo. So in that case, when you connect your eVideo network to LTE, at that time, HRPD serving gateway of eVideo will be talking to the LTE core network, EPC. For example, PGW, it will talk to the PCRF. So in that case, HSGW acts as BBERF. But other than that, do not worry about BBERF. Okay. And what is the use of default EPS bearer? That is covered in the first session. And as Dan mentioned, we are recording all the sessions. So feel free to listen to session number 1. But the short answer is default EPS bearer is to give the user always on experience. So when you power up the device, you will have at least one default EPS bearer with some default access point name. As a simple example, let's say you are Verizon subscriber, then Verizon.com would be an access point name. So when you power up, you have connectivity with Verizon.com. Okay, so it gives you always on experience. You can do email and web browsing type applications right away without worrying about quality of service. Okay, but session 1 will give you a lot of details on EPS bearer. We want to make sure that we focus more on the content for session 2. And feel free to stay after the normal session is over and I will answer additional questions. Okay, so that was the difference between guaranteed bit rate and non-guaranteed bit rate. And let's talk about a variety of QoS parameters. So we have several examples here. Okay. So QCI, one parameter QoS class identifier that will basically correspond to 9 different levels of QoS in LTE. Okay, and I will summarize some characteristics from one of the tables that we have. Then we have ARP. Allocation and retention priority. So basically, it says what kind of priority we need to give to a specific application. So for example, let's say we have a lot of email type users. Okay. And we are fully utilizing all the radio resources. So we have no more resources left for any new service. Now, some folks start making voice or IP calls. Now, voice or IP should have higher priority than email, because in the email application, we are not worried about the delay. Our email can wait in the buffer for a little longer time. We do not expect email to arrive within fraction of a second. We are okay if email has a couple of seconds of delay. So in that case, ARP for voice would be having higher priority than email. So when we have new voice or IP calls coming in, we have to make a room for those new calls. So we would perhaps downgrade the email data rate. We would put email in the buffer for a little longer time. So we are giving higher priority to voice or IP. So ARP tells us that what is the priority of that service. So when we are allocating radio resources, what is the priority? A retention priority. In the worst case, we may have to even eliminate some bearers, email bearers, because we simply do not have radio resources. So ARP basically dictates what kind of priority we need to give to a specific application in terms of radio resource allocation, in terms of prioritizing that compared to other services, in terms of retaining that session. And an EPS bearer may have guaranteed bit rate. It may not have any data rate guarantee. If we have to guarantee some data rate, then we will say what is that guaranteed bit rate. So for voice or IP, 12.2 kbps. Okay, and then we have maximum bit rate. Okay, MBR, maximum bit rate. So when you have multiple applications going onto the same bearer, then what is the total bit rate we would allow? That is the maximum bit rate. In case of default EPS bearer, which is a non-guaranteed bit rate, we may have again many applications onto the same default EPS bearer. So what is the total bit rate, aggregate maximum bit rate for that EPS bearer? Now remember one thing. In LTE, the quality of service is controlled at the bearer level, not at any other level. So if you have two applications with two different QoS requirements, you need to place those two applications onto two different EPS bearers. Okay. So if you have two applications but same QoS requirements, then it is possible for you to put both such applications onto the same EPS bearer, because you can give that bearer certain QoS. But if you have two different QoS requirements, you must have two different EPS bearers. Okay. Okay, now there is one question that we got for the GBR, AMBR. Okay, why does it utilize resources? Okay, as you can see from here, whenever your EPS bearer is of GBR kind, you have to guarantee some bit rate. Okay, that's this parameter here, GBR, guaranteed bit rate. So you are guaranteeing at least some data rate. Let's take one specific example. Let's say video streaming. So we may guarantee, let's say, 300 kilobits per second. Okay. But sometimes we say, okay, maybe there are multiple applications, and we'll say, okay, sometimes it can go even up to 1 megabits per second. Okay. So we will guarantee at least 300, but maybe sometimes 1 megabits per second. So we will allow up to 1 megabits per second. Okay. So maybe some high definition video, high quality video we can watch for some time. Okay. But we will have at least medium quality for 300 kilobits per second, something like that. Or you can view from another perspective. You may have multiple applications with some guaranteed bitrate, and together we will have certain maximum bitrate. So it depends. It depends on the applications and things like that. So hopefully your question is answered. AMBR is, as you can see, for non-guaranteed bitrate. So it's a more appropriate parameter to talk about in the context of non-guaranteed bitrate. Okay. But if things are not clear, feel free to have an additional question. ARP, we got one more question on ARP. Is it only allow, disallow, or it could adjust? So ARP, allocation, retention priority. So retention and allocation, both. So whether we can completely disallow or eliminate that or not, so that is one thing. Also, we have different levels. So we may downgrade the data rate. I think there are about 15, 16 different priorities. At least 15, I think. We have 15 different levels of ARP. So yeah, there are various degrees of ARP. Okay, so we can play with the data rates essentially. We can adjust MBR. So that's a good point. We can adjust the data rate. Yes. Okay. And again, thank you for your questions. It will help not only you, but your colleagues. And if I do not know the answer even better, then I can do some study and find the answer for you. That way my knowledge will also increase. So please continue asking questions. Okay. Let's say what is the provision for the user? See, our HSS SPR has subscriber profile. Okay. So inside that we would have various parameters. That okay, if the user connects to some APN, vzw.com, AT&T.com, this is the maximum bitrate we would allow, AMBR. And for services, let's say voice or IP, what should we allow? So guaranteed data rate, GBR. So an operator would have to come up with these rules for MBR, GBR, AMBR, all those things for a given subscriber. So all the parameters that you see, the operator needs to think about those parameters and decide those for a given operator. In the initial deployments, they may keep it simple, but as time passes by, you will see more and more complex QoS rules inside the PCRF. Okay, so let's talk about 9 levels of QoS. Okay? Okay, so let's take an example of QCI number 1. What does it mean? QCI number 1. What is the meaning of that? QCI 1 means that the bearer that we would have, the EPS bearer that we would have, would be of GBR type, guaranteed bit rate. So there would be some data rate guarantee. Okay. It is up to the operator to define the guaranteed bit rate for a given application. So for some application, voice or IP may be 12.2 kbps. For example, let's say voice, it may be 12.2 kbps. If it is some kind of streaming, maybe 300 kilobits per second. So it is up to the operator to decide for different services what they want to allow. So GBR, some kind of data rate guarantee, but the exact number, it is up to the operator, up to the application. So QCI 1, for what application we should use QCI 1? Voice, conversational voice. So regular voice or IP calls that is provided by AT&T, Verizon, etc. So operator provided voice or IP. We are not talking about Skype or Yahoo Messenger type voice or IP. That would probably go over the default bearer. We are talking about voice or IP that operator is aware of. Okay, so you have subscribed to voice or IP from Verizon, voice or IP from AT&T. That kind of IMS control, operator control service. Now, for QCI 1, we are aiming for a delay that is less than 100 milliseconds. Now, where is that delay? This is end-to-end delay between UE and PGW. Okay. So end-to-end, one-way delay. So from UE to the PGW, less than 100 milliseconds. From PGW to the UE, again, one-way delay, less than 100 milliseconds. QCI 1 means that the packet error rate that we are aiming for is 0.01, 1% error rate. Okay. So out of 100 packets, if we lose one packet, no problem, because our ears cannot differentiate between 0% error rate and 1%. Both qualities appear identical as far as our ears are concerned. So we are aiming for 1% packet error rate for QCI 1. And QCI 1 finally has second highest priority. Okay. The only thing that has higher priority than voice is IMS signaling. What is this IMS signaling? This is SIP signaling that we use to set up calls, to call setup, session setup. So when you are setting up a voice or IP session, gaming session, streaming session, whatever it may be, we want to set up the session very, very quickly. So session setup signaling has the highest priority, but other than that, voice or IP has the priority. Let's take one more example. Let's say QCI number 9. What does it mean? It means that the bearer associated would have no data rate guarantee, and we can put email, web browsing type applications onto QCI 9. The delay that we are aiming for is much more relaxed now, up to 300 milliseconds. So you can compare that 100 millisecond with the 300. Right? So our email packet can be waiting in the buffer for a little longer time. However, the error rate requirements are quite stringent. One packet out of 1 million packets. Right? We are aiming for very, very low packet error rate. The reason for that is we do not want to have too many TCP retransmissions. Otherwise, our air interface can support 300 megabits per second. But because of TCP retransmissions, the user perceived data rate may be very, very low. So for that reason, we want to have integrity of the data. So the error rate is very high. Priority is very low. So if we have email packet in the buffer SIP signaling in the buffer and voice over IP packet. Then IMS signaling gets highest priority, then voice over IP second highest priority, and then we have still some resources left. Then we will take care of priority 9 for QCI number 9. Okay, we have got a couple of questions, so let's take care of those. Okay, if the call is between two different operators, who guarantees bit rate? Good question. See, the QoS that we are talking about here is between UE and the PGW. Let's take a simple example. Thank you for your question. So, one UE is talking to its own operator. This is the EPS bearer, and that's where we control QoS. And let's say internet. There is only one internet, the internet. Okay. And then we have PGW number 2, UE number 2. So this is operator Y. So as far as QoS is concerned, this UE will work with its own PGW to have QoS, negotiation, control, whatever you want to use. And this UE will work with its own PGW to negotiate its own QoS. Okay. So UEs work with their own networks to provide QoS up to that point. Okay, up to that point. Because remember, when we say end-to-end QoS, what are the ends? UE is one end, and the PGW is the other end. So we have two ends. So QoS is controlled only between UE and the PGW. That's where we can really control QoS. We can have data rate guarantees. We can have delay control, latency control. Once the packet leaves the network, once the packet leaves our PGW, then we are just relying on these routers in the internet. Okay. We are hoping that they will give us a suitable priority. Okay. But as far as the strict QoS control is concerned, it is only between UE and the PGW. So UE has to work with its own side of the connection, its own network, to have the control over QoS. So hopefully this is clear. Let's see if we have anything else. Would you map application services to QCI? Effectively, yes. So let's go back so that I can summarize that concept again here. What this table shows is recommendations from the standard. Okay? And we have even given you the reference number 23.203, which you see here on the corner. Okay, in the standard 23.203, this PCC document. So we are seeing this table, which is from that specific standard. So these are recommendations from the standard. So normally what would happen is when we start using some application, which is IMS application, part of the operator's services, then that will be associated with one of the QCIs. And who does that mapping? PCRF, right? PCRF. So let me go back to that slide. Yeah, you see here PCRF, right? Rules function. So it got our SIP signaling. So it knows that, oh, this is a voice or IP call and it needs this kind of QoS. And it will decide that, oh, that application I should have QCI 1. Okay, QCI 1. So that determination was made by PCRF. Okay. based on the application requirements, based on the subscriber profile. And once the rule with those parameters is created, the PCIEF will make sure that if there is a need, we will have a new bearer. If there is already some bearer existing, then we will just add that application onto that bearer. So now we have multiple applications running onto the same bearer. Maybe because both the applications have the same QoS requirements. If you have different QoS requirements, we will have different bearers. So we control the QoS at the bearer level. So if two applications have two different QoS needs, we will have the need for two bearers, okay, two EPS bearers. Oh, looks like we got many more questions. Okay, yeah, let's take care of those. Okay, end-to-end delay. Okay, see, when I say end-to-end delay, as far as the standard is concerned, we are guaranteeing the delay if we are guaranteeing between UE and the PGW. That's it. Okay? It is only applicable between UE and the PGW. Once the packet leaves the PGW, wherever it goes, we do not quantify that in LT. So again, end-to-end delay that you see in the table, that QCI table, that is only between UE and the PGW. Yeah, so user perceived delay is different. But what we can really control, what the standard allows us to explicitly quantify, is between UE and the PGW. What if some user roams to operator Y? Okay. So we have basically the home PCRF providing rules to the visited PCRF. So your home operator will give the rules to the roaming or visited operator's network. And again, effectively, the home network controls the QoS. So as long as there is a suitable roaming agreement between two operators, we are okay. But again, home network provides IMS services. Home network provides control over QoS. The PCRF that controls QoS would be in the home network. And finally, another question, simultaneous voice and data, two different QoS or one session with data. Oh, if you have simultaneous voice and data, then your voice will be on one bearer, one QoS, and data will go to another bearer, another QoS. Okay, so two bearers at the minimum, two bearers. Okay, at the minimum. Okay. Now, one more topic related to QoS. For that, let me go back to our journal. Okay. Let's talk about QoS. So basically, we have the radio bearer. I'm writing fast, so hopefully you can still decode my handwriting. We have E node B. S1 user plane, that is your SDW, and PGW. Now, what is this? This is IP network. Again, IP network. And we have routers along the way. Okay. So, as far as the air interface is concerned, we have reserved radio resources. If you remember from a previous series, we have resource blocks. right? So we can reserve enough number of resource blocks to guarantee data rates, etc. But within the IP network, how do we really control QoS? Well, in the IP world, we use so-called DIPs, or differentiated services, and there are some code points, DIPs or code points, right? So that will make sure we can have certain quality of service. So we have certain recommendations from IETF on what kind of code points we should use for what kind of service, so that those IP routers can provide correct forwarding treatment. Meaning, if we have some high priority packet, it should be forwarded quickly. Let's say voice or IP. We will use one value of DSCP so that we can quickly forward the packets. On the other hand, if you have email type service, we will give that another value of DSCP so that it can wait in the buffer if the router is too busy with other high priority services. So when a packet arrives at the IP router, it will check what kind of DSCP is present in the IP header of that packet. So if that DSCP happens to be value X, the router will quickly forward the packet. On the other hand, if the DSCP happens to be some value Y, then router knows that it does not need to quickly forward the packet. If it is busy, then it can place that packet in the buffer for a little longer time. So in summary, in the IP world, one dominant way of providing quality of service is by forwarding the packets slowly or quickly, and to help us do that, we have DSCP values. So in the slide, what we are seeing here is some recommendations from Internet Engineering Task Force, IETF, and it says that, okay, if you are using service, let's say voice or IP type service, then we should give that high priority, and in that case, we will use, let's say this value 46, expedited forwarding. Expedited. As soon as that packet comes, our router will make sure it will quickly forward that packet. On the other hand, if you have some email web browsing type service where you do not worry too much about the delay, it will be default forwarding DSCP value 0, maybe what we would choose for that IP packet. So those are example applications. So for the routers, the operators would have to figure out that, okay, what kind of DSCP we should choose for a given application. Okay. Now, one more thing before we move forward, and I know there are some questions. We will answer those as well. But I need to give you one more important piece of information before we move forward. Okay. So now we have to figure out this DSCP value, right? So who decides that? So here is the basic idea. Okay. So who decides DSCP? Okay. So basically, whoever inserts an IP packet into an IP network. Okay, an example. Let's say downlink data transfer. Okay. So from the outside world, some packet arrived. This is the internet. Let's say some email packet arrived. And here is the private network of the operator. Okay. Here is the serving gateway. So now the PGW is inserting that IP packet into the private IP network, and here are the routers. So to tell the routers that they should give certain forwarding treatment, DSCP marking needs to be done by PGW, right, for this downlink data. Similarly, the SGW has to mark the value so that E node B gets the packet quickly or slowly. Okay. That is the idea. Okay. Similarly, in the uplink, right, our UE would need to figure out that if I have certain application, right, then that application needs to go onto a specific radio bearer. Okay, and that radio bearer corresponds to certain EPS bearer. So depending on the application, some will go into bearer 1, bearer 2, etc. Actually, bearer numbers start from 5, bearer 5 or 6 or 7. So that determination is made by the UE as far as the uplink is concerned. Okay. So uplink IP packet, uplink IP packet. Okay. So DSCP marking needs to be done by E node B. Because E node B has to tell the routers, can those packets wait or they need to be forwarded quickly. Okay, now let's take up those questions and then we'll have a short break. Okay, does the UE know about QCI? So when the UE gets the original IP packet, right, then in the IP header there would be some DSCP value. Yeah, that is possible. In fact, for the uplink, we may even give so-called traffic flow template, and I will talk about that little later. But yes, it is possible for the UE to know the DSCP, yes. And okay, so for the uplink, yes, UE could insert DSCP, yes. For the uplink, UE could do that, no problem. And where is the mapping for QCI and DSCP? Again, all the IP nodes, E node B, SGW, PGW, right? All the IP nodes, whoever puts IP packet into some IP network, they need to know the table. Okay, they need to know the table. Okay, let's have a short break. I will give you 10 minutes. Take care of those. The bearer goes over GTP tunnels. So who marks the DSCP in outer headers? Again, it depends on who put that IP packet into the IP network. So when the packet is going from PGW to the serving gateway, then the PGW would be in charge of that. And when packet goes from serving gateway to the E node B, then the serving gateway would put that DSCP value. And the router is supposed to perform marking, not E node B. Marking between QCI and DSCP, not E node B. See, as far as the E node B, serving gateway, and PGWs are concerned. Okay, let's go to some slide that gives us all those links. Okay. See, as far as the QoS is concerned, from the LT's perspective, what we need is QCI and the parameters shown here. We need QCI, ARP, GBR, etc. So when we set up the bearer, then all those parameters are decided. So PCRF digitize the rule, QoS rule, and then MME will help us establish these EPS bearer. It would have the link radio bearer, S1 is airplane, S5 SH. Okay. So once those links are established, then logically we already have QoS. But the only thing is, since our packet is traveling through the IP network, right, then what is the meaning of GBR, right? Because as long as you have enough bandwidth between node serving it, or you do not have to worry about guaranteeing some data rate. Right? How do you guarantee data rate in an IP network? Right? That's difficult. So as long as you have done some over provisioning, then we are okay. So the only thing that we are now trying to control is delay. In terms of delay, a router can either the packet quickly or slowly. So that's why we have to have some kind of mapping between the QCI and DSCP. Okay, so for a given bearer, IETF says that, okay, if it is a voice or IP type bearer, then let's say QCI1. See, there is no direct mapping. No one will ever give you direct mapping between QCI and this DSCP. You have to come up with your own table based on these recommendations. So let's say you are AT&T, you are Verizon. Then as an operator, you have to come up with some kind of rules. These are recommendations. So you have to figure out, okay, voice or IP? From the IETF's perspective, that should go to DSCP number 46. And now you have to read 23.203 that says that voice or IP is QCI1. So now you have indirectly merged the IETF recommendation and 3GPP LTE recommendations. Similarly, gaming. Right? Now you have to go to the table. Let's go to that table maybe here. So where is the gaming? Okay, so we have real-time gaming here and interactive gaming here. Right? Then you have to figure out that which of the two you will use. And accordingly, you will come up with QCI3 or QCI7. So it is again operator's decision. And then we will put that QCI7 or whatever QCI we get from the table onto CS4. Class selector number 4. And DSCP value is 32. So you have to, as an operator, you have to do this kind of mapping. Okay. So it is operator specific. For the application, these are the recommendations directly from application's perspective. But for LTE, you have to come up with your own table as an operator that this service is this QCI, and this DSCP. And that kind of mapping needs to be made available to all the IP nodes, eNode Bs, serving gateways, PGWs, etc. Okay. And can each node change? See, it is nodes from the same operator, then the same table, same rules are given. So that is not a problem. Okay. So DSCP X is received, Y is sent forward. Normally that should not happen because the operator would have configured the nodes. So if it's the same operator, eNode B serving it to PGW, then same treatment, there is a chance that serving gateway of one operator connects to PGW of another operator. Then there is possibility of some mismatch because the table is proprietary. QCI DSCP exact mapping is up to the operator. So there is a possibility that there is some disconnect. Okay. Okay. So hopefully you got answers to your questions. Now we have a couple of polls coming in. So I will give you a couple of minutes on this one. And this is like open book exam, okay? So feel free to look up in the PDF file when you are trying to answer the question. Open book, open Google, closed instructor. You cannot ask me, but other than that, no problem. 30 more seconds. Okay. Let's look at the results. Okay, so about 60/40. Okay, so we are setting up data connection. So we have the default bearer. No QCI is associated. Okay, so this statement is actually false. But let me tell you why. Okay, let's go to that table. Okay, see, if you look at this QCI 9, right, it is non-guaranteed bit rate, meaning the data rate is not guaranteed. So it may be 0 kilobits per second sometimes. Okay. These are the characteristics. So we are aiming for a delay less than 300 milliseconds between UE and the PGW. The error rate quite stringent, right? 1 in a million packets. That's our error rate target. Lowest priority. Okay. So we cannot say there is 0 QoS, right? We are still aiming for certain delay. We are still aiming for certain error rate. So even though it is like best effort service, email, web browser, still there is some QoS. Even though there is no data rate guarantee. Okay? There is no data rate guarantee. There are still guarantees of some other QoS parameters. Okay, so the name is little misleading. Okay, default bearer is little misleading. Okay, now for the next one, look at the table. Okay, look at the table, that 9 QCI value table, and then tell me if you want to do SIP signaling, which is IMS signaling. See, IMS has chosen SIP as the protocol for signaling messages. So for SIP IMS signaling, what QCI should we use? I am not talking about the voice medium itself. I'm not talking about speech itself. I am talking here only about signaling messages to set up the call. SIP signaling. There are two different things. SIP signaling is one thing. That is like call setup signaling. We have a session coming up later in the series that will talk about how to set up a voice or IP call. So there will be a lot of signaling messages. But here I'm not talking about traffic itself, only signaling messages. Okay, 30 more seconds to go. And feel free to look at the table, okay? You do not have to memorize everything. Okay, let me show you the results. Okay, so 60% got it right. QCI 5. Why? Again, let's go to the table. Okay, so if you see this IMS signaling, okay, where I have written that SIP is the protocol we have chosen, session initiation protocol, that is to help us set up a call. And for that, we have QCI number 5. That has the highest priority number 1. That's, yeah. Okay, let's go to the next folder. Now I am talking about real speech. the vocoder is creating the samples for your speech. So your real speech. For that, what is the QCI? "45 seconds. And thank you for participating in the polls. And also thank you for the questions. So once we are done with this, we will give you an opportunity to ask a question using the audio bridge if you choose to do so. Okay, let's look at the results. Much better, close to 90%. Got it right? So yes, QCI number 1. Okay, so again, same table. As you can see, the conversational voice, that kind of application is using the QCI value number 1. Okay, so that's that. So Diane, about the audio bridge.
Yes, if anybody would like to take the opportunity to ask a question on the bridge, you would use a *7 to unmute your line. You can do that now, and then *6 would mute it again. So anybody who would like to do that, who's on the bridge, *7 will unmute your line. You can do that now.
So if you do not want to type, this is your chance. I will wait for 30 seconds.
Just gives you another option to ask the question. As Nisha said, if you want to avoid typing, prefer to answer or ask it.
And we are recording the session. So you will be immortal. Your voice will be there for many, many years to come. Remember, LTE, long-term evolution. So whatever we are recording is valid for a long time. So be part of history. Looks like they are happy with typing. No problem, no problem. If you prefer typing, please continue doing so. Okay, so let's get back to our slides now. Okay. So TFT, what is this TFT? Traffic flow template. So here is the idea. Some packet comes in from the outside world. Now, pretend that you are a PGW. And some IP packet comes to you. Now, your job is to figure out where to place that incoming packet. Should it go to this bearer for this user, this bearer for this user, another bearer, another user? Right? So basically, where should the IP packet be placed onto? Which bearer, which user? That is the question, and answer to that question is given by TFT, Traffic Flow Template. So TFT is basically some kind of table, and I will show you an example. And that table helps us answer that question, that whenever this packet comes, maybe this specific packet should be placed onto this bearer for this user. Okay? Because our PGW would have thousands and thousands of bearers with many, many serving gateways for many, many users. So we need some kind of table that says that, okay, observe the headers of the IP packet, and based on the content of that IP header, we will figure out that, oh, this is a packet for user number 2, and user number 2, there are 3 bearers. Out of those 3 bearers, X, Y, Z, the packet should go on to EPS bearer Y. That kind of answer is given by the TFT. So we may use things such as the IP address, source IP address, destination IP address, source port number, destination port number, things like that, which are present in the IP header. We will use that knowledge to make that decision that, okay, the packet should go on to a specific GTP tunnel corresponding to a specific EPS bearer. So let's take an example. Okay. So here, this is the table that we have. Where is this table? Right now, this table is at the PGW. Okay. So some packet has arrived from the outside world. It's a voice or IP packet for, let's say, user equipment number 1. So then we look at the table. We look at the destination IP address. Let's say IP address X. That's what we have given to user 1. And IP address Y. That's what we have given to user number 2. So that's our 2 IP addresses. X for one user, Y for another user. So when we look at the IP header, that is for user 1, we will find a match with IP address X. So we now know that, okay, we have those bearers 1, 2, 3. Those are our potential candidates. That our packet should go on to one of those 3 bearers, 1, 2, or 3. So now we need to go a little deeper inside the IP header and look at the port number. Okay, port number, let's say for some video session, port number 1000, let's say. Another video 1001, voice or IP, let's say 2000, something like that. So we look at the destination port number for that incoming packet. So let's say we find that the destination port number is 2000. Then we find a perfect match here that for these specific user IP address X, now we have found a match with the port number. Destination port number. Destination port number 2000 means this is a voice or IP application, and hence the packet should be placed onto EPS bearer number 2. Where is bearer number 2? Okay, here is bearer number 2. So then the PGW will place that voice or IP packet onto bearer number 2, which corresponds to a specific GTP channel with some serving gateway. So we need the TFT at the entry points. So from the outside world, when the packet comes, PGW has to have TFT. So for the downlink, we need TFT at the PGW. For the uplink, the UE has to decide where that packet should go. Packet should go on bearer 1 or 2 or 3. So UE has to do that in the uplink. So UE will have TFT for the uplink. Because UE has to decide the traffic flow template for uplink. Okay. So that has to be done by the UE for the uplink. Okay. So this is what is happening. We have, and you might have observed, but when you ask a question, I will quickly send you a positive acknowledgement. K means okay. So I will respond to your question at a suitable point in time. Okay. But I will send you a quick acknowledgement. So here is the idea. PGW, the outside world, is sending an IP packet, and we have this TFT, traffic flow template, that makes our job easier. Put that onto this barrier number 1. This is the GTP tunnel between the serving gateway and the PGW. From this GTP tunnel, we will put the IP packet onto another GTP tunnel towards some E node B, and E node B will put the IP packet onto a specific radio barrier. Okay. So let's say this is GTP tunnel X, GTP tunnel Y. So E node B knows that whenever it gets an IP packet from GTP tunnel Y, it should put that IP packet onto radio barrier number A. Similarly, if there is another application, then GTP tunnel, let's say B here, that is decided by TFT. And then if GTP tunnel B here, the associated S1 barrier, another GTP tunnel, let's say C, and that GTP tunnel C corresponds to radio barrier number D, something like that. So that is happening for all the downlink packets. Same way, if there is an uplink packet for some service data flow is your application. So if there is a packet like that, let's say I have a video streaming packet, and that corresponds to radio barrier D. This is the radio barrier D. So the uplink traffic flow template would say that, okay, my application is video associated with some port number. Then that video will be placed onto radio barrier number D, some GTP tunnel, some other GTP tunnel, and then it will go into the internet. Okay. So as you can see, where is the TFT? For the downlink, PGW puts that packet onto some GTP tunnel, onto some barrier. So for the downlink, PGW has that TFT. That is here. For the uplink, the UE has to decide where the packet should go, which radio barrier. So that is for the UE. And in between nodes, E node B serving gateway, very, very easy. They just have mapping between the radio barrier and the S1 user plane barrier, between the S1 user plane barrier and the S5 barrier. So their job is relatively straightforward. Okay. Let's answer the question that we have got. Is the port number always correspond to specific service? Yes, that is correct. Absolutely correct. How about the destination address? Yes, so for the downlink, let's go here. See, for the downlink in our simple example here, IP address X is for one user, IP address Y for another user. So based on the destination IP address, we know whether this is for UE1 or 2. And then for a given UE, then we can go a little deeper and look at the port numbers to further figure out exactly which barrier that service corresponds. So yes, destination IP address also very, very important for TFT. Okay. And if there is something else in your mind when you are asking the question and the answer doesn't seem right, then just have a follow-up question. But yes, destination IP address is one of the important TFT parameters. Now, in LTE, we may have given you many IP addresses. Okay, it's possible that more than one IP address is assigned to a given UE. So then we will have multiple IP addresses for that. Looks like there is one more question. Oh, two questions. What is filter precedence? Filter precedence means what kind of order we should use when you are trying to figure out the mapping for a given packet. So if you see let's say okay, in short, filter precedence, it is the order in which we should evaluate those TFT parameters. So I would first, okay, let me use some other numbers, okay. For the purpose of illustration, okay. A, B, C, D. A is the first row that we will use, first rule. So first we will check that, okay, for that UE, what is the part number? Is it 1000? If the answer is yes, then we have found the bearer number. If the answer is no, then we go to the next one. Another precedence, B. Is the port number 1001? No? Okay, let's go to the next rule. So we check port number. Is it 2000? No? Then we go to the very last row of the TFT template for the user. So if nothing else matches, then it will go to the default EPS there. So filter precedence is the order in which we should apply the rules. So if rule A is satisfied, then we no need to evaluate B, C, and D. Okay. So if A is not satisfied, if we do not find port number 1000, then only we go to the next row in the table for that UE. So filter precedence is the priority or the order in which we evaluate those roles, TFT roles, basically. Okay, good. Thanks for the question. In the last slide, destination address is not mentioned. Oh, yeah, we were just giving examples. So source address, destination address, source port number, destination port number. Just examples. So we are not trying to give you a full set of parameters, just examples. But yes, destination is very important. Okay, so it looks like a couple of more questions we got. What is the relationship between TFT and QCI? Okay. When we set up a bearer, okay, let's say for voice or IP, then the PCRF decides that we should get QCI number 1 for this voice or IP session. And also when we are exchanging those SIP signaling messages, we would say that, oh, we will exchange medium, voice or IP, voice traffic, speech, using port number, let's say, 2000. Now, that port number 2000 is given to the PCEF. So let me go back to that. Yeah, here. I mean, this is better. Maybe the other one is better. Yeah. You see here quality of service rule, right? QCI number 1. So along with that, we could say for the purpose of TFT, we will say port number 2000 is for voice or IP. So now we create an entry for the TFT. So until this point, there was no entry in the TFT table at the PGW. But now we are setting up a new bearer for voice or IP. So at this point, PCEF, PGW will create a new entry, a brand new entry. That, okay, in future, there will be a voice or IP packet coming. And the port number, destination port number will be 2000, destination IP address, specific IP address, let's say address Y. So now PGW knows that in future when a packet comes with destination IP address, destination port number 2000, there's the bearer carrying voice or IP for that user. Okay. So in terms of QCI, there is no direct relationship between QCI and TFT. However, as part of the QoS and policy rule, we have to identify the service flow, service data flow, the service to the PGW, and TFT is included in that kind of rule. Okay, how does call from UE to the PGW look like? You are showing PGW to the UE. Can you show the other way, UE to the PGW? Okay, sure, we can show that. No problem. Okay. So we have UE. We will have some service with port number, let's say 2000, and then the radio bearer number. So port number 2000, let's say is this one, voice or IP. Let's say this is some kind of video. So that corresponds to bearer number D. And then port number, let's say 3000. That is for radio bearer number A. So when the UE application video or voice or IP generates an IP packet, the UE will look at that IP header. Then what kind of IP packet is it? Okay, this IP packet has destination source port number is better here. The source port number is let's say 3000. It is generated by a video session, for example. This is video. So it means I should put that onto radio bearer A. On the other hand, if the UE sees that the application is voice or IP, then in that case, it would be port number 2000, and it says port number 2000 is a voice or IP packet. It should be placed onto bearer number D. So it will put that packet onto radio bearer number D. So UE just needs to figure out the radio bearer number, and then it is easy. eNodeB looks at the radio bearer and it will map that onto a GTP tunnel C. SDW GTP tunnel C is mapped onto GTP tunnel B, and then the PGW will send that into the internet. Okay, hopefully you got answered your question. Okay, now this question, okay, is little tricky. Okay, so please think. I will give you, let's say, 3 minutes for this one. I have not given you a direct answer to this question, okay? So you have to think little more. So I will give you 3 minutes. So we have the default bearer. I will give you a hint. Look at that QCI table, okay? QCI table. That's where your answer is. So we have the default bearer. Then we have SIP-based voice or IP call. So what do you think? The number of bearers. And it is a trick question, okay? The answer is not straightforward. You have to think. Thinking is good. So go to the QCI table and see that default bearer, what kind of QCI you need. For voice over IP call, do you need just one bearer or you need more than one? That is the hint, okay? Voice over IP. Is one bearer good enough or you need maybe at least 2 bearers. Think voice over IP signaling. Think voice over IP traffic. Think QCI for default EPS bearer. If you can answer those 3 questions, you should be able to answer this one. One more minute. Okay, let me share you the results. Okay. 53% got it right. Okay, 3 bearers. Okay, we would probably have 3 bearers for the UE. Now let me tell you why. Okay, let's go to that QCI table. So looks like that QCI table, there is a holy grail. It has a lot of answers. Okay, so let's see. Okay. See, default bearer, right, for internet access. So we can give one bearer for web browsing, maybe QCI number 9. Okay, so that's for internet access, no problem. And then for voice or IP call, to set up the call, we need QCI 5. So let's say QCI number 9 for this one. And then we need QCI number 5 for SIP signaling. Okay. And finally, to carry the real traffic, we need QCI 1. In LTE, we control the quality of service at the bearer level. Anytime we have different QoS requirements, we have different QCIs. Here we need 3 distinct QCIs, number 9, number 5, and number 1. 3 different QCIs. It means we need at least 3 EPS bearers. Okay. So 1 would be default, and 2 would be dedicated. 1 dedicated for SIP signaling, another dedicated for real voice or IP traffic itself. So 3 is the correct answer. Okay. The SIP signaling does not go away. Yeah. And for a default EPS bearer, yes, QCI 9 is allocated. Sometimes QCI 8. So QCI 8 or 9 is allocated to the default bearer. So you can think like QCI 9 as your default QCI. If you want to think that way, no problem. Okay. So it was a little tricky question, but that's the answer, okay, based on what we have seen. Okay. Now, we have talked about the nodes of PCC, PCRF, PCF, etc. We talked about the concept of QCI and even TFT. Now, let's put all those pieces together and summarize how we can provide quality of service when we use PCC. Oh, looks like there is some question, so let's take care of that before we start this new topic. Good question. At what point the SIP signaling bearer gets set up? Now, it is up to the operator policy to decide when to set up the SIP signaling bearer. I will give you one real-world example. Okay. So Verizon Wireless has this so-called open access, right? So you can look at their website for open development. They got 700 megahertz from PCC, so they have to follow certain rules, more transparency. So if you look at their requirements, then their UE connects to the IMS network upon power up. Okay? So then during the, let's say, power up operation, attach operation, we set up the default bearer with the IMS network itself. Okay? With the IMS network itself. Now, if we want to do SIP signaling, then we need to have a dedicated bearer. So normally they would set up the dedicated bearer for SIP signaling right during the attach operation. So after the default, they will immediately have dedicated. Okay? And once it is there, it will be there for a very, very long time. Okay? Even if the user goes idle, no data activity, a part of that default and dedicated bearer with the IMS network would still exist. Okay, so it is supposed to be there for a very, very long time. Normally there are some keep alive timers, maybe 30 minutes or so, but we typically renew that. So not basically for all practical purposes, you can assume that it is there all the time. The default bearer is there, dedicated signaling bearer is there. Now, let me give you a more accurate answer to that question, because we didn't get a chance to go into the specifics. Okay, I was just expecting answer from the material that we covered here. Okay, but if you look at the real world deployment, okay, then you will see something like this. Okay, what you will see next is more in line with current commercial deployment. Okay? This will give you a more accurate answer. So what is happening here is the following. Let's say you want to have a voice or IP call, okay, which is controlled by the IMS network. Then we must have default bearer. Okay? That's the requirement. You cannot have just a dedicated EPS bearer. You have to have some default EPS bearer with the IMS network. So let's say your access point name is IMS network. Okay. So a PGW that is in charge of that IMS network has a default EPS bearer with the UE. Okay. This is always there. So if you are doing connectivity with the IMS network, then you will have at least a default EPS bearer with the IMS network. Then we need a dedicated EPS bearer. So this is a QCI number 8 or 9. Dedicated EPS bearer. This is SIP signaling. So this is another bearer, right? And to carry the speech samples, we have another dedicated bearer. And we have 3 different levels of QCI. So that's why we need 3 EPS bearers just for some IMS service such as voice or IP call. Okay. And if you want to connect to the regular internet, so access point name is, let's say, internet. then you need another default EPS pair. Okay. So the most accurate answer to the question that I asked is 4. There will be 4 EPS pairs. Okay. Because for internet, there will be a different access point name. Okay. And that's the normal way we operate the system. So with an access point name, you must have a default EPS pair. So here we have 2 default EPS bearers. One with the IMS APN, another one with the internet APN. Therefore, the correct answer is 4. But if you tell me 3 based on the material covered here, it would be acceptable. But in the real world, you will see 4 because there will be different APNs for IMS and internet. And with each APN, you must have a default EPS pair. And of course, you can never have a stand-alone dedicated EPS bearer. A dedicated EPS bearer cannot stand on its own feet. It needs help from the default bearer. So you must have a default EPS bearer. That is a prerequisite for a dedicated EPS bearer. Okay, that's comprehensive information so that you get the most accurate view. Okay, confused about the bearer. Okay, bearer carries something. So there could be signaling message over that bearer. There may be a bearer that carries real traffic. Okay, so in LTE, when we say bearer, it doesn't necessarily carry only user traffic such as email, web page. A bearer may be a signaling bearer. A bearer may be user traffic bearer. So in LTE, bearer does not mean only user traffic. So your access stratum, radio access, and non-access stratum signaling, that is over signaling radio bearer. And for the data radio bearer, it may be SAPE signaling data radio bearer, or that data radio bearer may be carrying the real email, web browsing, and voice or IP bits. So hopefully that is clear. So bearer could be for anything, could be for signaling, could be for real data. Okay, let's go back to QoS implementation. So we'll put together all the pieces that we have talked about and figure out how to provide end-to-end QoS. Okay, so as I mentioned earlier, in LTE we have chosen to use SIP protocol, Session Initiation Protocol, for session setup, session modification, adding some medium. We were doing voice call, but now we want to add a text message, we want to add a video, etc. So modify the session, we want to tear down the session, maybe the call is over. So for all those things, we use SIP, Session Initiation Protocol. That is our protocol. So as part of the SIP message, in this example, we have so-called invite message. Inside the invite, we have SDP, Session Description Protocol. Now, can you tell me what is inside the SDP? Just 1 or 2 examples. What does SDP contain? You can answer through Q&A box. What is inside SDP? Session Description Protocol. We have 60 students, so at least some should have the answer. Ideally, I want 62 answers, but at least some. Okay, it looks like my begging has some effect. Okay, very good, very good. Codec? Yes, for example, what kind of codec we are supporting? Adaptive multirate is the one we have chosen. How much bandwidth? Very good, very good. So priority, we have port numbers, very good. We have the IP address, excellent. Thank you very much. So those kinds of things are present inside the STP, port number, IP address, so that we can give that as part of the TFT to the PCEF, PGW, we have the supported speech codec, AMR, what kind of bandwidth, what kind of data rate, all those things are inside the STP. It describes the requested quality of service. So that message finds its way to the proxy, call session control function, which is the IMS element. And then gradually it goes to the UE. Okay? So if you want to be exact to the proxy, it will go to the PGW, PGW to the serving gateway, E node B, and from E node B over the add interface to the UE. So our SIP message has now found its way to the UE. And the UE looks at the invite message, STP, and says what kind of codecs it supports. And I will talk about more about voice or IP in another session. Here we just want to make sure you know how to tie together QoS and session. So UE says, okay, I support that kind of codec, AMR codec, 12.2, I'm happy with that. So that will be in the message 183. There's the message code for SIP. It is session progress. That is the interpretation of 183, session progress. So now a proxy looks at what the other party, maybe there is another UE or some kind of IP phone. So now it says, okay, this guy says 12.2 AMR, this guy says 12.2 AMR. So we have found the common ground. So let me make sure that the user has subscribed to that kind of application. So it will send a diameter message, AAR message, authentication authorization request message with the PCRF. Now that interface is RX. So the RX interface between the application function and the rules function, it helps us extend those diameter messages. We can ask that, has the user subscribed to that kind of application? Should this call move forward, or we need to block that call? So then the PCRF, okay, will come back with the answer, authentication authorization answer, that okay, no problem, that the user has subscribed to that. And in between, we have not shown here, but because of the real estate problem, we are running out of space, but we will have talked to the HSS and asked HSS that give me the subscription profile. Has the user subscribed to voice or IP type service or not? Things like that. So we have got that knowledge, and now we have agreed to provide that service. And that is the answer given to the other party here. Okay. Now, since we have decided that the call should move forward, then we have to give the rules to the enforcement function. So PCRF will use the GX interface to provide the quality of service rule. So we would say here that QCI number 1 for that service, and we want to guarantee some data rate, because QCI 1 meaning it's the guaranteed bit rate. So we have to specify what is the bit rate we are guaranteeing. So let's say 12.2. So that kind of rule is given to the policy and charging enforcement function. And next, we set up the bearer, end-to-end bearer between the UE and the PGW. So if we do not have any existing bearer with that kind of QoS parameters, then the PGW would initiate setting up of a new dedicated EPS bearer. And of course, the bearer has 3 components. We have the radio bearer, S1 user plane, S5, S8. we need help of MME. MME will work with eNode B and the serving gateway so that we have end-to-end new dedicated bearer setup to carry this kind of voice traffic. So as you can see, we have various messages. We have SIP signaling coming into the picture. We have diameter protocol coming into the picture. We use those interfaces RX, GX so that we can get the authorization for the service. We can specify the rules to the PGW. So that is the high-level view. In the next couple of slides, we give you some additional parameters for those messages. But that is the overall view of providing end-to-end QoS. And remember, when we say end-to-end, what are the ends? UE is on one end and the PGW on the other end. So we are controlling QoS really between UE and the PGW. Okay. We have got one question. So let's see. SIP session is a bearer. They cannot be monitored at eNode B. Yes. SIP signaling messages, yes. They are not observed or processed by eNode B. That is correct. The source of that SIP signaling message, let's say UE, and the destination is proxy, call session control function. So if UE wants to send the SIP signaling message, source is UE and destination is this proxy. So all the other nodes in between, they do not do anything. eNode B will forward to the serving gateway will forward to the PGW, and PGW will forward that packet to the proxy, because proxy is the destination. Okay. So that is that idea. So you are right. eNode B doesn't go into the SIP message. It doesn't say, oh, this is a SIP invite message. It doesn't have to worry about that. Okay, then there is one more question. What is the difference between QoS initialized by UE and initialized by network? A good question. In LTE, only the network can initiate the setting up of a dedicated bearer. UE can never say that give me a new dedicated bearer. The only thing UE does is when the user clicks on some IP application, gaming, voice or IP, whatever, that results in some SIP signaling, such as invite message. And that invite message will find its way to the IMS network. Here, AF, application function, proxy, CSCR. And then proxy to the PCRF to the PGW. And the PGW really decides that, oh, I need to set up a new dedicated EPS pair. So UE can never say directly that give me new QoS for this new application. The only thing UE does, SIP signaling exchange with the IMS network, and that will result in setting up of a new bearer if required. So there is only single QoS that is determined, controlled by the network. So the parameters are really decided by PCRF based on the subscription profile, based on the requested QoS from the UE, which is inside the SDP of a SIP message. That's the idea. Okay, so QoS request is processed by the PCRF rules function. And based on the subscription information that we got from HSS, SPR, PCRF makes the decision. So there is only a single QoS, not two different QoS from the UE side and the network side. Okay, one more question. Standard QCI 129, where are they defined? In the eNode B and the PGW only? QCI 129. you mean to say maybe what you are trying to figure out is who needs to know the QCI sort of mapping, application and the QCI. So PCRF is the main entity that is figuring out QCI for a given service, given application. So PCRF needs to know that QCI values, PCRF decides QCI for a given application. And eNodeB just gets the QCI value from the serving gate. Actually, if you want to be more accurate, from the MMA, because we are setting up the dedicated bearer. So it just knows the QCI because it is specified by MME as part of the dedicated bearer setup. So eNodeB doesn't figure out that QCI 1 means voice over IP or voice over IP means QCI. It doesn't need to make that decision. Now, in terms of using that information, that okay, QCI 1 means I have to have certain delay. Yeah, eNodeB will know that. eNodeB needs to know that table so that it can guarantee some data rate, not data rate, but error rate. It can guarantee some error rate, and it can guarantee some latency by using the QCI table. So the QCI table itself, yes, it is known to the eNodeB because it needs to manage the radio resources. But it doesn't decide that for this application we should use QCI value X. The value of QCI is decided by PCRF. And the table is in the standard. The table is defined in the standard 23.203. So it is predefined in the standard because those are standardized characteristics. But it is known to the eNodeB. It has to be known because that's the only way eNodeB knows whether to aim for short delay, longer delay, what is the error rate that I need to guarantee override interface. So eNodeB needs to know the table, but it doesn't decide the value of QCI. Only PCRF does that. Okay, so you should have got answer to your question. Okay, let's go to the next. So the next couple of slides, we are just going into some more details. For example, over that RX interface, right? The proxy says that, oh, this user has some media description. This is basically from the STP, right? 12.2 kbps, etc. AMR speech. We are just describing the medium, and then the PCRF will say yes, this is okay or not. Authentication, authorization, answer. So we would say that okay, this is what we accept, and identify how to identify the specific service for future reference. So basically, here the PCRF has decided QCI and yes, no, whether to allow that service or not after communicating with HSS. Okay. So to be more specific, we use this diameter protocol. Whoever sends a request, that is called a client. Okay. Whoever gives the answer, that is called server. Okay. So PCRF acts as a diameter server, and those are the diameter message names. Okay, authentication, authorization, answer, and basically we are just trying to make sure that subscription is okay for that user. GX, that is the rule for the QoS. So the PCRF is giving that rule. Okay, in so-called AVPs, attribute value pair. So in a diameter message, we will have so-called AVPs, some fields, message fields are called AVPs, and here is the information about QoS, 12.2 kbps, for example. So that kind of rule is given, the name of the message, re-authentication request, and this is the request for QoS. So we are defining the rules in the diameter RAR message, and this is the acknowledgement from the enforcement function that yes, I have received those rules. If we do not have such QoS already available in an existing EPS pair, then we will create a new session, meaning new EPS bearer for that new service, new application. As far as the rule itself is concerned, policy and charging control rule, here we are specifying information about QoS, information about charging. Okay. So, rule identifier, let's say rule number 100. Okay. So we have rule number 100, and that rule has several things. For example, how to detect service data flow. Okay. How to detect service data flow. The service data flow is your application. Okay. So, for example, if it's a voice or IP type call, okay, video call, then there will be some port number. Let's say port number 2000. So this is just an example, okay? Just an example. So port number 2000. So that's what the UI application decided, that I want to use port number 2000. And it will be as part of the template. TFT, traffic flow template, STF template. That voice or IP corresponds to this port number. And there will be some IP address associated with that, IP address X. Okay. So for this UI specific IP address, this port number is the application. And we will give the priority, precedence, that if we have several rules, right, the TFT rules, then which is the priority? What is the order? So should this be looked for first? Should we try to find a match with this rule first? Or this rule has lower priority in terms of search? Okay, so that is the PCC precedence, and the template is this. Basically, in future, when a packet arrives from the outside world, then the PGW knows that, oh, this is user IP address X, and this is the port number 2000. It means this is the voice or IP application. So at this point, we create the TFT entry. So in our table, at this point, the PGW creates an entry. A new row in the table is created that says destination IP address, source IP address, port number, etc. So this will help the PGW detect a service data flow. And then how to control the QoS. Gate status. Is the gate open or closed? Should we let that IP packet pass through or not? So if the user is subscribed to that, we will say yes, the gate is open for that service. If the user has not subscribed, we will say the gate is closed. QCI. Here is where QCI is specified. Right. So who decides QCI value? PCRF. So PCRF says, okay, this is voice or IP. Let me put that onto QCI value 1. Then what kind of data rate we are guaranteeing for the uplink and downlink? So guaranteed bitrate for uplink, guaranteed bitrate for the downlink. What is the ARP? Allocation and retention priority. So if we are running out of resources, can we downgrade? Can we eliminate? That is the ARP value. I think 15 values are there. Okay. And then what is the maximum bitrate? So even though the guarantee is up to certain kilobits per second, Maybe sometimes we will allow data rate to be higher than that. So uplink maximum bit rate, downlink maximum bit rate, etc. So this is all about QoS. Now charging. How should we charge the user? So charging key, let's say value X, service. So sometimes we want to identify the service. Maybe we want to charge FTP service one way, or streaming. We may have video streaming for many packet data networks. So if you want to combine all the streaming applications for many APNs, we can do that. So it identifies the service. Then we have the charging method. We will talk about that toward the end of the session. So is it online charging? Is it offline charging? What kind of charging is it? Then the measurement. Measurement means maybe you want to charge based on amount of data, or if it's a voice or IP session, then the call duration is important. We are not worried too much about the data rate itself. Okay. So what are we measuring? Application function record information. This is just, for example, application number. If it's not too critical, application IMS network may give some number to that service. And if we are trying to get a report based on service identifier, so as I said, a video streaming, right? You may have multiple packet data networks, and we have video streaming sessions for all those APNs. Then we can combine all the streaming session information into a single report for the purpose of charging. So if you want to do that, we can do that. That is allowed by the standard. So in summary, we are specifying these kind of rule, PCC rule, to the PCEF, because PCRF creates the rule, and it is the enforcement function that is really enforcing those QoS parameters. So we have information about QoS, information about the charging. So those are the two kinds of information present in the PCC rule. Policy rule, charging rule, those are the two kinds. Policy meaning QoS. Okay, we have got a couple of questions, so let's take care of those, and then we will have a short break. Okay. Can two applications use the same port number? See, let's say you are a UE, okay, and you are using two different applications. So by nature, you will have different port numbers for different applications. Okay. Now that is when you are generating some traffic. Now, if you are trying to access some server, okay, let's say web server, FTP server, then they have fixed port numbers. So let's say port number 80. So all the service requests for, let's say, web browsing, that will be processed by web server for the web browsing application. So there are some standard port numbers, okay, and the reason behind port number being different for different services is that's the way we can identify, is it web browsing application or email application. So there are some port numbers that are standard, web browsing, email, and those are used for the servers, because those software pieces, they check, is anyone sending me web browsing request? Is anyone sending me email request? So we have specific port numbers, FTP, I think 2021, something like that. Web browsing, HTTP protocol, hypertext transfer protocol, I think that is number 80. So we have some fixed protocols using fixed port numbers. But some applications will just dynamically create non-standard number in some range. So the idea behind port number is to separate applications. Okay, so two applications will have two different port numbers. Then ADP. Okay. What is this AVP? Attribute value pair. So let me just give a simple example. Maybe we can go to, there is some rule. Yeah. See, this is a diameter message. Okay. This one is called re-authentication request. So there are many message fields. Okay. So in the diameter message, there are different fields, message fields. And those fields are formally called AVPs, attribute value pair. IETF is very flexible. So you can keep adding different AVPs so that you can extend the scope of that message. So in LT, when you want to provide QoS rules to the PCS, we will use this AVP called QoS information. So we can specify the data rate, QCI, whatever, things like that. So the AVP is basically, they are the message fields in the diameter protocol. Okay? And we can define many different kinds of AVPs to take care of the functions that we want to perform. That is the idea. Similarly, let's say here we have AVP, so-called media component description. So as part of that, we will say, okay, this is the data rate requirement, things like that. So is the message field, nothing beyond that, just a message field. Okay. So hopefully that is good enough. If it is not, ask another question. So AVP, attribute value pair. Okay, attribute value pair, and we have hopefully covered that in the list of acronyms. We have two more questions so far, and we will answer those and then have a break. Non-standard, only the PCRF and eNodeB need to know QCI definition. This is a little tricky, see. So in general, yes, operator can define their own QCIs, but the problem is that what is the meaning of that? Right? We need to define it somewhere. So the application that is generating traffic, right? So that application needs to know what am I using, right? So for gaming, we may have some application. So let's say not gaming. Gaming is sort of standardized. But let's say operator has some proprietary type service, and they want to have QCI number instead of 129, maybe QCI number 20. So then they have to define that QCI 20 interpretation of that. So UE vendors, they would need to sort of know what kind of information they need to guarantee for the purpose of uplink. Normally, application servers in the IMS, they are in the best position to do this kind of proprietary stuff, because in IMS network, application server is the one in charge of service. Okay? So if you want to have the QCIs that are sort of non-proprietary, that are proprietary and not standardized, non-standardized, then PCRF needs to know. So that is correct, as you pointed out. eNodeB needs to know. That is correct. That is correct. And those are the two main entities that will use QCI directly. Maybe, yeah, so that should be good enough, because even though UE may ask for some QoS, we can always override at the network. Yeah, so I think you are right. PCRF and eNodeB, probably that's more than good enough. Now PGW is just getting the QCI value, so it doesn't need to worry about the interpretation. Yeah, it just enforces, so you are right. Okay, yeah, so you are right. PCRF and eNodeB should be good enough. Okay, PCC rule credit control message. Oh, see, PCC rule. Okay. So rule has several fields, several types of information. And here we are giving you some examples. Okay. So if you are interested in the rule, you can go to the specification document 23.203, and then you will get many other references. But credit control request answer, that is just one set of messages. There are many messages. So if you look here, for example, see the name of the message, re-authentication request, re-authentication answer. If you look at the RX interface, it is AAA, right? So it just depends on what we are trying to accomplish. So PCC rule doesn't mean that it is only credit control request answer. It could be anything. Okay, it could be, there may be many things. For the charging also we may have another set of messages, etc. So if you are talking about GX interface, in fact, on the GX we have RAR and RAA as the messages. So it depends. It depends. Credit control, I have seen, if I recall, that is when we have interworking between LTA video, then I have seen those kinds of messages. The diameter messages, credit control request answer. But for LTE, for the scope that we are considering here, RAR, RAA, those are the messages. There's there. Okay, time for a short break. So again, 10 minutes. About the need to know QCI interpretation. So who should know the meaning of QCI? So a student said that who are the nodes? So E node be PCRF, right? Are they the only ones, right? And I thought, and I said yes, but I thought a little bit more, and I think at least PGW would need to know the interpretation of a proprietary QCI, and this is why I think that way. The PGW has to decide the DSCP value for an incoming IP packet, right? So if we know QCI, which is let's say which is a non-standardized, which is a proprietary value, then to figure out what DSCP to use, we need to understand the meaning of that QCI. So if you use QCI number 15, some of our own proprietary value, then that has to correspond to some DSCP. So PGW should know that table, the meaning of QCI table. So he should have that. So E node be PCRF, they need to know. And at least PGW should know that table for the purpose of DSCP marking. Now, serving gateway, maybe we can get away without touching the serving gateway. If serving gateway is just copying the DSCP, then it doesn't need to have that table. So, for example, if serving gateway gets a packet that is marked with DSCP X, then when it leaves the serving gateway, it can keep the same DSCP. So it can do copy and paste. Then it doesn't have to worry about the exact interpretation. But I would suspect the operators would have some table that is also known to the serving gateway. But at least E node the PCRF and the PGW should know the QCI interpretation. And PGW because of need for DSCP marking. Okay, if you still have some additional thoughts or comments, let me know. Let me give you an opportunity of using the audio bridge. So again, *7 to unmute, *6 to mute, So I will wait for 30 seconds. Anyone who wants to use the audio bridge? Okay, then we will continue with the presentation here. Okay, so I mentioned earlier that we have a so-called subscription profile repository, but typically it would be part of the HSS because HSS has the subscriber database, okay, and then we know what kind of QoS the user is subscribed to. Now that interface between the PCRF and SPR is sort of optional. The standard doesn't say much about that interface, but we could have things such as the profile request going to the HSS, asking for the subscriber profile. We can have identity of the subscriber that will identify who the subscriber is. So IMSI is one example of the subscriber identity. And the HSS would come back with the response what services user is subscribed to, if we have any guarantees of any QoS, what is the maximum limit on the QoS data rates, things like that. So basically, we get information about the subscriber now available at the PCRF. So we can make decision and create a specific quality of service rule. Okay, so now we will discuss how a dedicated EPS bearer is established. So assume that our UE has created some SIP signaling message such as invite, and that has found its way to the application function, which is proxy in the IMS network. Now that goes over, let me try to be more accurate, dedicated EPS bearer for SIP signaling. Remember we said we should use QCF5, right, for SIP signaling. So let's use that dedicated bearer to carry the SIP signaling messages. And once the proxy has processed the SIP message, it will give the information on the QoS in the form of STP to the PCRF through RX interface, and then the PCRF will give the rule to the enforcement function PGW via that GX interface we talked about briefly. Okay. So basically, the QoS rule has arrived at the PGW enforcement function. Then it will check. Okay. Do I have any EPS bearer that is currently capable of taking care of that QoS? So if we do not have any existing EPS bearers that can provide such requested quality of service, then we have to initiate setting up of a new dedicated EPS bearer, and that's what PGW is doing. PGW is asking the serving gateway, please create a new EPS bearer, and the serving gateway will forward that to the MME. MME will work with the eNode B so that we can set up a new bearer. The bearer request has now reached eNode B. eNode B will check, do I have enough radio resources to support that quality of service? assuming that we have enough radio resources available to meet the QoS requirements, then we will reconfigure the RRC connection to add a new data radio bearer. So it can carry user traffic. Then we have S1 user plane bearer, new S1 user plane bearer, and new S5, S8 bearer. Okay. So those bearers are established when the responses to the request are received. So now we have aimed to add EPS bearer between the PGW and the UE. And this new dedicated bearer is able to meet the QoS requirements for the new application that we just started. But remember, in LTE, we control QoS at the EPS bearer level. So even though we talk about applications, if two applications have two different QoS requirements, we have to map those two applications onto two separate EPS bearers. If we have same QoS requirements for two services, no problem. We can put both of those same QoS applications onto the same bearer. So email, web browsing, we can put those two applications onto the same default EPS bearer. But there is still some QoS, QCI number 9, so there is still some QoS. It's not zero QoS. There is some QoS even for QCI number 9. Okay, we have got one question. Preemption priority, is it different from allocation retention? Let's go to the specific yeah, see, this is just between HSS and PCRF. So the concept is the same, right? But the name of the parameter is different. So here the HSS is that in general, this service, okay, can we preempt for something else? But ARP is much fine resolution parameter, right? We have, I think, 15 different values, so you can degrade the service to a lower rate, things like that. So here this is just the name of the parameter, and you will get the exact QoS parameter a little later. That is part of the PCC rule, which should be on the GX. Yeah, here is that rule. So the exact value for the from the perspective of QoS, that is here. Okay. So we will have to somehow map some preemption priority onto some ARP. So that kind of mapping is done by the PCRF. So the concept is the same, but the parameter names are different, and probably there will be some kind of mapping that is done by the PCRF. Okay. So that is the high-level view of how to set up a dedicated EPS bearer. And next, we will just go into the details of all these steps. Okay. So let's say the bearer has been set up. Then how is the packet flowing through the network? So the packet comes from the outside world. This is the internet, let's say. Another packet has arrived at the PGW. Then we will use the concept that starts with T. And that will help us figure out that that packet should be going over a specific bearer, a specific GTP tunnel. What is the name of that concept? Okay, something allows us to figure out that the incoming IP packet should be placed onto bearer number 3. What is that concept? The name of the concept starts with T. So can you tell me what is that concept? Okay, let me see. TFT, very good, very good. TFT, traffic flow template. So TFT will look at the fields of the IP header, destination IP address, port numbers, etc. to figure out that, okay, that packet should be going over a specific GTP tunnel. And this is the IP address of the serving gateway, this serving gateway. And how do we identify the GTP tunnel endpoint ID? Tunnel endpoint ID. Once the serving gateway gets the packet, it says, oh, incoming tunnel endpoint ID X. So it means the outgoing is tunnel endpoint ID, let's say alpha. And that's corresponding to this side of the E node B related GTP tunnel. Now, E node B gets the packet on tunnel endpoint ID alpha. It has a table. It says, if I get a packet on tunnel endpoint alpha, I should put that onto a specific radio bearer. So this way, the UE has received an IP packet onto a specific radio bearer that corresponds to specific application. Because bearer and application, they have a specific relationship. Same way in the uplink, we have the UE putting the IP packet onto a specific radio bearer. E node B gets the packet from a radio bearer, it will put that onto some S1 user plane bearer, which is tunnel endpoint ID, like that. So now it is going in the reverse direction. So this is how the packet can flow from one node to another node. We have a couple of questions. What are the functions of PCRF, HSS, and IMS server? Functions, okay. So let me write journal, and you will get a copy of this. So PCRF, so basically creates quality of service and charging rules. For example, decides QCI for an application. It decides the data rate. If we have to guarantee some data rate, maximum bit rate, things like that. So that's PCRF. And then you ask for HSS. HSS just subscriber database. So it knows what the user has subscribed to. Authentication information is inside HSS. And then we have application server. So basically it is in charge of services, applications. So it's possible that we have one server that takes care of voice or IP, and we have so from call session. See, we are not showing all the interactions. I will show you little more interactions with IMS later. But from call session control function, it can go to application server. So one application server is in charge of voice or IP. So SIP signaling will go like that. Then gaming, we may have another service, another application for SMS, presence. So if you look at Verizon's website for LTE open access, then they are aiming for SMS presence type service for IMS network. So we can have application servers that are designated to provide specific services. So SIP signaling messages will find its way to the application server. So if you want to add another voice call, add video, add text message, etc., the application server has those kinds of capabilities to enhance the bare bone call. Okay, so that's that. So the beauty of those application servers is that third parties can develop innovative applications, and we can just put that in the IMS network, and all of our subscribers, millions of subscribers, can access the same application overnight. Very, very easy to rapidly and cost effectively deploy new services. That is the advantage of an IMS-based services network. Okay, three-way voice over IP call would require two different dedicated bearers. Three-way voice over IP call. So let's see. We have, here is the UE. See, as far as the PGW is concerned, we have, let's say, some kind of application server. So that can probably serve, now we are talking about new voice over IP. So probably QCI, let's say 1 for traffic. And 5 for signaling. Yeah, so we should have, yeah, one that is good enough. Okay. Yeah, so if we have a three-way call, then probably application server should be able to combine traffic. And from the user's perspective here, yeah, one should be good enough. As long as there is an entity that is combining the traffic, for a three-way call, we should be okay. UE1, UE2. So in my opinion, yeah, this should be good enough. Over there interfaces, from the EPS perspective, between a UE and the given PGW, one bearer should be good enough. Okay. Okay. So let's get back. So this is how the traffic is traveling between the UE and the PGW. So basically we are using radio bearer number, tunnel endpoint ID, IP address of nodes to help us move the traffic through the network. Again, quick summary. Basically, how do we control QoS? We really control QoS between UE and the PGW because that's where our EPS bearer is, right? And the radio bearer, how do you control that? Radio resources. So eNode B scheduling algorithm is in charge of that. It will allocate appropriate resources to maintain the data rates, latency, etc. This is an IP network. Again, IP network. So what we have, differentiated services. So we will use the help of DSCP values to make sure the routers give a suitable forwarding treatment for the packets. Okay, time for a question. Okay, I will give you about 2 minutes, 2 to 3 minutes for this question. So whoever needs to put the IP packet into some IP network, that entity has to choose the DSCP. So choose the best option. Okay. One more minute. Okay, almost 60% got it right. eNode V, serving gateway, and PGW. So if you think about the downlink, packet comes from the outside world, PGW has to do DSCP marking. So packet has come to the serving gateway. Now serving gateway has to do DSCP marking, so packet can go to the eNode V. Because remember, we have IP network between eNode V and the serving gateway PGW. If you think about the other direction, uplink, right? Then in the uplink, when UE sends a packet to the eNode V needs to mark that IP packet with DSCP, so that serving gateway gets the packet, right? So eNode V, serving gateway, and PGW, those are the best options here. MNE doesn't take care of traffic, so no need to worry about that. Application function just processes signaling message, so no need to worry about that. Okay. Now charging. There are a couple of questions related to charging. So hopefully now once we are done with this topic, you should get more comprehensive view of charging. Okay. Offline charging, online charging. So basically, offline charging, think of this like end of the month bill. That is the simplest example of offline charging. Okay. Meaning, when we use some service, maybe voice or IP call or web browsing, whatever, we do not worry about the dollars at that time or euros for that matter. We just get the service, and once we have used the system, used the services, at the end of the month we will send the consumer a bill, right? So the service that we get, right, does not depend on any credit that we may or may not have, right? Is the bill that is generated at the end of the month after we have used the service. That is offline charging. Online charging means we will check first. So when we make a call, then the system will check. Has this guy basically, does this guy have enough money in the account? Because it's like prepaid calling. So let's say we have $50. So $50, maybe we can talk for 1,000 minutes. So we will get some authorization for a few minutes first. So we want to make sure that we have enough money in our account, prepaid account, so that we can use the service. So if we keep talking, and maybe sometimes there is not enough money in the account, then we will not be able to use the service. So that's the idea. So offline charging means there will be a bill generated after we have used the service. So as part of the offline charging architecture, we have these various entities. So we have policy charging enforcement function, charging trigger function, charging data function, charging gateway function. Okay. So basically what is happening here is that charging trigger function means it says, okay, call started, that is one event, let's say 10 o'clock, and call ends, let's say 10:10. So those are the events. So whenever some events occur, the charging trigger function, it says, oh, there is a trigger, some event has occurred, call has started, call has ended, something happened, and then it will tell the charging data function that this is a call start time, another event occurred, call end time. So that kind of information is received by the charging data function. Then the charging data function will create a record, charging data record. So it has a specific format, and it will say start time, end time in a specific fashion. Standard defines the exact format. Okay, so it will have some kind of, okay, so we subtract that, say 10 minutes or whatever, things like that, and that information is given to the charging gateway function. So CDF, charging data function, it is basically generating these records in a specific fashion. And then we pass the CDRs to the charging gateway function. So this guy will verify that is this the proper format or something is missing, maybe the data is corrupted, the CDR has no end time or whatever. So if there is some problem, then we will generate error messages. Otherwise, we will say, okay, this is okay. Sometimes we may have to reformat a little. It depends. But assuming that the format is okay and there are no errors, then we will provide the potentially modified CDRs, so-called refined CDR. This is my own term, okay? So we just make sure that CDR is okay, validated. Yeah, maybe that's a better term. We validate the format. So then it goes to the billing system, to the of the operator, and then this will generate a bill for the user. Okay. So that is the idea. So we are basically using the services, and once the service has already been utilized, then we have CDR generated and billing taken care of by some external network. So what is our LTE doing? So in LTE, our PCEF, which is implemented by the PGW, it acts as this called trigger function. Okay? That some event has occurred. So let me then inform the CDF. Now, in the offline charging scenario, this C called charging trigger function is PCF. Charging data function is also in PCEF. Okay, charging PCEF. Okay, so we can then say that from the PCC's perspective, both these functions are inside the PGW. And the charging gateway function will then make sure the validity of the CDR. So PGW acts as PCEF, and PCF will do the functions of charging trigger function and charging data function. Okay. And we use the diameter protocol again, okay, to forward those charging data records. Some example messages. So here we have, now if these are just implemented by the PCEF, then this is internal. Then there is no need to expose that. But if two separate boxes are doing the functions of charging trigger function and charging data function, then you would see these kind of diameter messages. So accounting request and accounting answer. Accounting request basically timestamps, start time of the call, end the time of the call, who is the user, what is the kind of service, voice or IP or whatever, and other entity sends the acknowledgement that I have received the message and the CDR has been properly created. But as I said, in offline charging, these are basically functions of PCES. So in LT, both of these are part of the PGW. Online means that before we get the service, we have to get authorization. So in this case, we have this PCES, which is of course implemented by PGW. So when some event starts, so let's say session starts, so then it will ask this online charging system, OCS, that give me authorization. So authorization request. So even before the voice services have been used, we have not yet started talking. Okay, before we start talking, we have to get authorization. So this is like pre-approval, right? Pre-approval. So this is like getting pre-approval for your new car or for your new house. Right? You have not yet bought the car, but you go to some banks and say, give me the pre-approval, so that when you really buy the car, you can get that money. Right? It is like that, pre-approval. So before we use the service, we say, okay, do I have enough money or not? So that pre-authorization, pre-approval kind of request will be going to the online charging system, and then we will check. There is the account balance management function. So it says, okay, I have $50 in the account. Okay, so that will be translated into certain number of minutes, for example. And they will say, okay, you got approval for, let's say, 30 minutes. Okay, so 30 minutes, we are okay. So we will allow up to 30 minutes call. And now the user keeps on talking, and we are reaching the 30-minute limit. Then we will get another request for reauthorization. So as you can see, during the call, we may be sending multiple requests to the online charging system, because before we provide the service, we need to make sure that there is enough money in the account. Then there is something called rating function. So this is basically if it's a voice or IP call, depending on what kind of service it is, let's say 10 cents per minute. And we get $50 amount here. If you want to be more accurate, we get some kind of monetary number here, and then we will ask this guy that I have $50 or whatever, how much is that worth? So we know the rating, right? How much per minute, and accordingly this guy says 30 minutes for some kind of dollar amount. So then we will tell this PCES that this is what we authorize the service for that much duration. So account balance management function basically knows how much money we have. The rating function has some kind of rating for the service, and now we reconcile to and inform the PCEF how much call duration is okay. Once the call is done, the session has ended, then we update the amount of money we have here, and then the charging gateway function is informed. Now this is all optional. There is no need to generate a billing record for online charging, because the user has a prepaid account. But if you do want to generate a CDR, then standard supports it. Okay. So it is optional, but it's possible to have the CDR generated. But the basic idea here is that before using the system, we get the pre-approval. Some example messages. So, credit control request. Someone mentioned the credit control information. So for online charging system, we can ask for pre-approval, pre-authorization, so credit control request. So the enforcement function is asking the online charging system, right, that I need to know how much call duration is allowed. So then the online charging system will work with account balance management function, the rating function, and give the answer that okay, we allow for certain minutes, and we now start the service. So periodically you see again another set of message. Okay? So periodically we get approval. Okay? There's the online charging system. Okay, let's answer some questions that we have got. Okay. So, okay. So we have some mapping defined in the standard. Let me just summarize that for you. Okay. So there is GV interface. So different documents have different interface names. So this is equivalent to GA and RF. A GY interface. Okay, that is equivalent to RO interface. Okay. So if you have different documents, then you will see different names being used. Okay, so there's that. Then where do the CDF and CGF reside? Yeah. So if you are doing this offline charging system, offline, then okay, let's go back to the offline. Okay, so in case of offline, charging trigger function and charging data function both are in the PCEF. It means in the PGW. Okay. Yeah, okay. So there's that. And PCF is PGW. Yes. In LTE, PGW acts as PCF. Absolutely correct. Okay. Oh, looks like a couple of more questions. Okay, why do we need a RF interface? What data is captured by the serving gateway? Oh, I think the standard allows multiple ways of collecting the information. So in my opinion, if you just have PGW, that is good enough. Okay, that is good enough because the packets will always be traveling through the PGW. Okay, so even the standard allows multiple options. I think PGW is good enough. PGW is good enough. And what they, so I am not aware of any specific information that will not be known to the PGW. So in my opinion, whether it is SCW, PGW should be good enough. Okay, because there may be a change in the serving gateway when the user moves, but your PGW is still the same. Okay, but standard does give us an option. Okay. Serving gateway. Now, someone has made a comment that maybe serving gateway is from one operator, PGW. So it is possible. as the student has commented, that okay, those are from two different operators. So maybe the serving gateway is from one operator. You are roaming into some operator's network. So the serving gateway in the visited network, roaming network, that can collect information about the amount of data uploaded, downloaded, whatever, and then provide that to the local charging system perhaps. And then that charging system can talk to the home network charging system. That is a good example. That is a very good example. Yeah, so probably that makes sense. So I would agree with that. Yes. Okay. But in general, the information is the same as GW, PGW. They have access to the same information. But this is a very good idea. Okay. And let's see if there is anything. PCRF and PGW. Oh, PCRF, PGW. Remember the rule, PCC rule, that says how to plot QoS, QCI, data rate, and in terms of charging, how do we want to charge the user, online charging, offline charging, what are we measuring, amount of data, or based on the time. That kind of information is sent over GX. Okay, thank you for your question. Let's see what we have. Okay, so a question for you. Who has the information about the money that we have? Okay, how much money? $50, $100? Who knows the amount of money in online charging system? Online charging system. This is the total amount, not just the authorized amount, but the total amount we have in our account. The total amount, okay? $100, $50, not just the authorized amount, but the total amount. Okay, so it is the account balance management function, right? It knows about the total money we have, and we will get authorization for a little smaller amount at a time. Okay, so thank you very much for your questions and answering some of my questions. We are reaching 12 noon, so I would give you some time to fill the survey form. I hope you learned quite a bit, and I will send you the soft copy of the notes. I'm not running away, I'm still here. So if you still have questions, feel free to ask. I will stay a little longer on the bridge also. Okay?
Thanks so much, Nishith. This is Diane Easter, and I'm just putting up the survey now for you to complete. Thanks, Nishith, for a good session today. As he said, I will be sending his whiteboard notes and the annotated PowerPoint file that he wrote on today, and everybody who's on live meeting will be forwarded that. So please take the time. All right, I got to re-put the web page up. Let me try that again.
Oh, I was able to see. Okay.
Oh, were you? Okay.
Yes, yes.
All right. Okay, but you will need to go into full screen mode to complete the survey, and then Nishith will stay on the line to answer additional questions if you still have them. You can either put them again in the live meeting Q&A box or use *7 to unmute your line. So again, looks like the survey's come up full screen. Thanks for taking that time to give us your feedback. It helps us to determine plans for future sessions like this.
And if they cannot see, they can get out of live meeting and come back, right?
That's correct. If you are having trouble seeing it, closing the live meeting interface and going back in helps. And if you're still having difficulty after you do that, IM me and I will send you the link directly.
And while I cannot use the journal or PowerPoint, I can see your questions that you are typing in Q&A box, and I will be able to answer. So feel free to send additional questions,
It says you are not authorized to view this page.
If you'd like, you can send me an IM and I will send you the link directly if you're still having difficulties. This is Diane Easter.
And also normally if you get out of the live meeting, if you exit and then come back, that normally solves the problem. Okay, we have a question for voice or IP features. How does the PCF know which, what features subscribe to, and how to charge? Very good, very good. Now, there is some kind of standardization work that is something called MMTEL, multimedia telephony, something like that. And as part of that, we have specified what services the user can access and how to implement those services using an IMS-based solution. So that is sort of the kind of mechanism that probably would become popular as time passes by. Currently, there is no voice on the LTE system supported by operators. So if you want solution right now, then you will fall back to legacy CS core network and use those services. But assuming that in future we go to voice or IP, then there will be this MMTEL kind of approach, and that will help us implement those features. Okay? And HSS SPR should have that knowledge. So in the subscriber database, we should have that information already stored. So PCRF should be able to get knowledge of that information. So then we know whether user has subscribed to that or not. And how to charge the user for a given service? An operator will define a rule, charging rule. There are some rules, and we can give some number. Rule number 1, charging rule 2, charging rule 3. And charging rule 1 may say voice or IP 10 cents per minute. Charging rule number 2, FTP, upload, download, $1 for 10 megabytes. So there would be this kind of set of charging rules which the operator would define in the PCRF. So now the PCRF knows how to charge a specific service that is being activated by a user through SAFE signal.